we're starting this new module right now, this new setup called set theory. Not a complete introduction. I'll give a start to it so that we can sort of get our hands dirty a little bit practicing it. All right, so set theory was developed in the 1960s and 70s by a theorist named Alan Fort. He was a musician and a mathematician. He was at Yale, and he just died in 2014, and unfortunately I never got to meet him because this theory is one of the coolest, most facile, usable theories for atonal music, okay? So sometimes you'll see that it's called Fort set theory, just to keep your knowledge, you're aware of that stuff. All right, so what I'm going to do is explain to you a little bit of the history behind why this theory came up. Now, it comes up in the 1970s, but it's primarily for looking at music of the early 20th century. So Schoenberg is one of the major composers that this, bless you, that this music, or this theory was invented for. Okay, Arnold Schoenberg was a Viennese composer, Vienna, and he's one of the composers that often gets clumped in with a group we call the Second Viennese School. Who's the first Viennese school? Yeah, all those great classic Germanic composers. And so Schoenberg and his students, Alban Berg, and anyone know the other one? Webern. And Anton Webern. Not Weber, that's very different. Webern. Okay, can y'all see that? So he's the teacher, these are the students. Schoenberg is largely self-educated. He is an interesting character that I'll tell you more about when we get closer to discussing the actual music, because today we're going to look at sort of the terms and functionality of it all. Okay, so Schoenberg is writing music like this, and as you know, I have this wild idea that we should link theory to music. All right, so this starts really quietly, and I want you to just sort of sit back and listen. We don't have a score at this moment because I want you to just hear it. And think about how dense and rich and chromatic this is, and think about any ways that you might possibly be able to analyze this with your current set of tools, okay? We'll see. That's enough for now. Okay. Anyone familiar with this music already?
Yeah.
Okay. Anyone remember what the words are to this?
Something about like black butterflies.
Yeah.
That's right. Giant black butterflies, sometimes translated as moths, are obscuring the rays of the sun. Yeah, it's a little creepy. Okay, so a little historical background on why this is so creepy. First of all, in Vienna at the turn of the century, this was written in 1911 and premiered in 1912. So around 1912, it's very in fashion to have dark things. Why? Anyone have any ideas? Vienna in the turn of the century.
Expressionism.
Expressionism, right. Does anyone know this term, expressionism? It's an artistic movement that takes real things but distorts them. And one of the most famous paintings you probably know is Munch's The Scream. Right? There's that skull-like creature, and it's kind of ghostly, but it's on a real bridge overlooking a real lake, and there's two real people in the background. So it's like this horrifying distortion of something. What else is going on in Vienna at this time? Psychology classes, anyone? Sigmund Freud, right? Good. We're beginning to learn about our interiors, our ids, and our secret and sacred desires that we didn't even know we had, right? So there's all this creepy interior stuff going on. And so this is very fashionable. Vienna is an intellectual hotbed at this time period. And so people are reacting to that. And so this is one of the reactions to, and Freud actually went on walks with Mahler and told him about the problems with his marriage. So it was all the intellectuals were hanging out together and sharing ideas, and the art was coming and flowing from these ideas. Okay, so we've got this piece called Night about the black butterflies. It's definitely expressionistic, and it sets very well in this time period. But did you hear anything you could link onto and say, oh, I know how to analyze that? Any thoughts? Now people are just going, not really.
There was almost a beginning of a fugue, kind of.
Oh, good.
And then it just stopped, and then it came in clarinet.
Almost the beginning of a kind of a fugue. Dee, dee, dee. And then another iteration of a dee, dee, dee. Right, good. Good. That's exactly what's going on, is that we're now looking contrapuntally, and almost the start of one is perfect description because it's only a 3-note set. It's kind of the cellular style of composition we looked at with Stravinsky, where there's a little set that gets manipulated over and over again to make the music. And that is called developing variations. It's kind of part development from sonata form and part variation from variation form, but on little tiny bits of music. Set theory gets invented in the 1970s to look at music that's atonal like this, that emancipates the dissonance, as Schoenberg liked to say. And so it's a numerical system. It's a system of looking at the interval content of sets and cells, as opposed to just, hey, here's the pitch C, and we want to get back to C by the end of the piece. So it's a set theory. It's based on cells or sets. Okay, I'm going to make some room here. You all have this, I assume? Okay, so for the beginning, what I want to do, and many of you predicted this was coming, C is 0, and we're going to be in a fixed do or fixed 0 system for the time being. I'm going to run out of room. We'll just go down here. You can see what I'm doing here, right? And you just finish it out chromatically all the way up to the top. You can go to 12, but it's basically just 0 again. It's like repeating the octave, right? So these are PCs. We've been calling notes pitch classes. Now we can call them pitch integers too. Integer is just a number, right? So 0 through 11. And we're sticking with a 0 system, not a 1 system, right? But we have a term called enharmonic equivalence. Enharmonic equivalence, which means that D flats also count as 1s, right? D sharps, F flats, etc. So any enharmonic is fine, we just give it the number. Because it's not a triadic system, right? We're not doing stacking tertiary chords anymore. So we have enharmonic equivalence, and we're just going to start to use the numbers. But for now, I'm going to keep these on the board because we don't have them memorized yet. I think I can probably squish a B up at the top. 10 is B flat, 11 is B natural, or their enharmonic equivalents. Okay, get rid of that. The second thing is we have octave equivalence. So a C so high that only bats can hear it, and a C so low that only whales can rumble it, is the same number. It's still a 0, no matter what. So we don't care about that. But that's similar to the music you know already. We often take a C that's high and put it into a chord, even though the E and the G are below, right? So we have octave equivalence in more traditional theory too. Okay. Now, we're going to take this set of numbers and we're going to reinterpret them, so I'm going to use a different color here, as PCI, which stands for pitch class intervals. Unison is a 0. Minor second is a 1. So what I'd like you guys to do is fill out the rest of the chart of possible intervals. And we don't need to go beyond major seventh. So go up to a major seventh chromatically. Just expand them with numbers. Go down here, 4 major 6. Okay, did you have all those intervals? Okay, now sometimes in some school classes, theories, you'll see this is written as a T and this as an E so that we don't confuse 1, 0 and 10 and 11. I'm going to keep using 10 and 11 and we'll just try to always separate them with commas or be clear about it, okay? All right, so now when you're using pitches and you want to transpose something, you have to sort of think in the key and move around and make sure you've got the right number of half steps. Well, that's all this is. It's just the number of half steps. And therefore, it makes transposing exceedingly easy. So let's say I'm going to use the set that you heard, the counterpoint set from that thing is an 013. And I'm going to put them in a little set bracket, like, I don't know how many of you have had algebra lately. But I don't want to scare you. I want to keep you grounded in notes because we like notes. But that's our set. And Schoenberg would have manipulated it. Just to be clear, Schoenberg did not invent this theory. He did not use this theory. He used the old-fashioned musical way. Fort comes along and makes a theory so that it's easy to analyze Schoenberg. So that's the order of things. But we're going to use this now, and we're just going to transpose this set, 013. And if I said, okay, I want to go up a major seventh, then all we have to do is add 11. So here's our major seventh. So we're going to add 11. It occurred to me when I was prepping this lecture that soon I'll have people who don't do math the same way. I'm going to have to rearrange my lectures when Common Core people come through.
Or not.
Or not, right? Or they'll just have to learn it my way.
Here's my high school math book. Read that.
And we're ready. Okay, 11, 12, and 14 is the answer, but that's above our red numbers, our pitch class numbers. And so what do you imagine we're going to do?
Start over.
Well, start over, kind of, yes.
Let's go back to the
Sure.
beginning.
Subtract 12, yeah. That's what we're going to do. We're going to subtract 12. We don't need to for 11 because it exists. But 12 minus 12 will be 0, and 14 minus 12 will be 2, if I've done my math right. So your new set, transposed, is 11, 0, 2. B, C, D. Yes?
So the 013 is for pitches, or is it like those two are the same, it's just one is marked as the intervals?
Right, that's a really excellent question, just to be really clear. The 013 are pitches, and then the numbers here are PCIs, pitch class intervals. So what I'm doing is I'm taking notes, 013, which would be what notes if we were just going to look at them on a staff? C, C sharp, E flat, or D sharp, depending on how you want to spell it. Then we're going to add a major seventh from the green notes. So that's the interval. And then the result is more notes.
Okay.
So I guess technically I could have put those in red right there, although I've already misplaced my red. There. So these are our new notes, okay, or pitch classes.
So where did you get 12 from? Like, why did you subtract 12?
Because that's a great question. Where's the number 12? There's 12 half steps in a chromatic scale.
So it's always 12.
It's always 12. It's called modulus 12 for the math heads in the room, mod 12. It means we're always going to be reducing it to under 12. 0 to 11 is what we're looking for. Okay, and 0 to 11, that accounts for that octave equivalence I was talking about. That's what we're doing here is octave equivalence. We're taking this into its base area. So I'll give you sets of numbers, which will stand for notes, and then we're gonna transpose them by various intervals using numbers instead of notes. And then you can go back to the notes and check to see if you think you got it right.
Wait, so if it went over 12, it would be a new octave?
Yeah.
But doesn't that screw up just the C is C no matter what octave you're in?
It does, but that's why we take away the 12 so that we put it back in that octave.
Okay.
Does that make sense? Okay. All right. So to be clear, once again, these are our pitch classes, or pitches, like we used to call them, right? Pitch classes, or pitch integers, we can call them. And we're going to stick with a set do or a set 0 on C. Then we're going to look at these intervals. These will stay the same always. These are always the interval numbers, the pitch class intervals. And we're going to add or subtract by these intervals to go up, or transpose down one set. Any questions? All right, let's try it out and let's see how we're doing here. What if I give you the set 0, 1, 5? So let's start with a set of 0, 1, 5 over here. And first of all, figure out what actual pitches those would be. Okay, Ashley, what are the pitches?
C sharp F.
C, C sharp, F. So our set's going to sound like this. Okay, I'm going to get rid of this confusing thing here. So now leaving this on the board with 0, 1, 5. I'm going to go over here. I'll make it green. Keep her. Okay, and I say, all right, let's go up A. Let me pick something. Let's go up a perfect fifth. We don't have to do anything but adding and subtracting, so don't freak. It's not going to get weird yet. All right, who thinks they have this? Marcus, you want to lead me through it? What do I do?
So you would just add your 7.
PCI of a 7. Good.
So that gives you 7, 8, 12.
Plus 7. And that gives you 7, 8, 12.
And you subtract 12 from the 12.
Mod 12, good.
Which is G, A flat, C.
G, A flat, C. Here was our original. Here's transposed up a perfect fifth. Great, easy, right? Okay, so that's all fine and dandy. What if you get a negative number? What if I say I want you to go down a major sixth? Let's try that. Same group, yeah.
I'm sorry, Dr. Guzzo, what interval did you say?
Down a major sixth. Good. Yes, when you go down, you subtract.
Could you also, no, you're gonna have to add the,
See if
you're gonna have to add 12 now to make it even. Yeah. This is why I'm
We should get math credit for this, honestly. Okay, down a major sixth. Anyone want to try and tackle and explain?
So you subtract 9.
Okay, so our number, we'll just check it out with our board. PCI is 9. Okay, so we need to subtract 9. Okay, so the resulting numbers are
Negative 9.
yes,
Negative 8.
negative 8,
Negative 4.
negative 4. Okay. Now to get those into the territory we need them in, what do we do next?
At 12.
Mod 12, exactly, at 12. So then what do we get?
You get 3, 4, 8.
3, 4, and 8.
Do you have to do it in that order, or can you automatically add 12 to begin with and then subtract the numbers you need?
If you're quick at this and you don't need all the steps, fine. Yeah, you'll get the same answer, but at least when I'm teaching it, I like to do it step by step so we can really see everything that's going on. And then if you don't feel comfortable with math, you can do it step by step. It's simple adding and subtracting, and you should be okay. All right, so what are our pitches now?
E flat, E, and A flat.
What were the original pitches?
C, C sharp.
Good. Okay. I'm going to give you a short list to do on your own, and then we'll report back and see how it happened. So I'll give you a couple more seconds. You're going to have to mod 12 it. I like to use it as a verb. I also think it should be the name of the band. With a mod 12, don't you know? We're from Liverpool.
Oh god.
See, I was thinking like German electronic.
Yeah, mod 12, yeah. The Icelandic, the main branch of the Icelandic record store is called 12 Tona. 12 tone. So we'll talk about that soon. That's not as funny if you haven't done 12 tone yet. Okay. What do we have? Who wants to do it? Katie.
I got a 4, 5, and 9.
4,
Wait, no, just
5,
kidding.
and 9.
3, 4, and 8. I read the wrong numbers.
Yeah.
3, 4, and 8. Explain how you got there.
Well, you would add 15 to each number, which
Right.
turns to 15, 16, and 20.
15, 16, and 20.
And if you do mod 12, you subtract 12 from each of those, which is 3, 4, and 8.
Do-do-do-do. Do we all agree? Everyone got that? Easy, you got it. Excellent. Okay, so that's the first introduction to set theory. And soon what we're going to do, and we'll continue this next time, because I think we're almost out of time for this segment. So what we're going to do is we're going to put it on a clock face, because that's going to make a lot more sense in the long run. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, C, C sharp, D,